Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be focusing in on vapor pressure. And one of the reasons why we're doing this is that it turns out that by measuring the amount of gas that is left a liquid, we can evaluate the strength of the IMFs. Because remember, in the vapor phase, we have no IMFs. In the liquid phase, we have lots of connections in between the molecules. So by breaking these IMFs, going from liquid to gas, and figuring out how easy it is to do, we can evaluate a lot about the properties of a material. And one of the reasons we can do this is if I leave a liquid out in air, some of those molecules are going to end up leaving and they're going to enter the gas phase. And this will just keep happening until we reach a constant concentration of those gas phase molecules. You're most frequently probably aware of this with if you leave a bucket full of water out in an open room, the air will become much more moist. If you run air over it, it will happen faster. And this is exactly how a humidifier works. Now, one of the biggest reasons why we're going to end up doing this and looking at that pressure of the vapor is because, remember, using the ideal gas law, we can relate pressure of a gas to concentration of a gas. And as a result, we can figure out how many molecules there are per liter of air available. And one of the big things is we're going to notice that this is going to depend exclusively on the IMFs of the liquid and the temperature, which gives us both a way to relate concentration to pressure and tells us how much energy it takes to break those IMFs. And in practice, how this works is, let's say we look at water. If I go ahead and put water into a flask with open air, there's no water molecules in the top of the flask. And so some of those water molecules are going to get adventurous and say, ha ha, there's room up there. I'm going to go up there. And so we're going to start having more of this water vapor in the top of this flask. And so what we're going to have is most of the water is going up and very little of it is condensing. However, the longer you leave this system going, it reaches what's called equilibrium. So we're having just as many molecules entering the gas phase as they are leaving the gas phase. And this is called saturation. And we're going to be talking about saturation a lot throughout the rest of the semester. So I want to keep an eye out for this idea. What it really means in this case is that we've put as many molecules in the gas phase as possible. We've reached a critical pressure, which means that we've reached a constant kind of concentration. So in order to first leave that vapor phase, which is that critical point, we're looking at more or less how easy it is to leave that vapor phase. We need to have enough energy to break those intermolecular forces. And it turns out that this is going to be related as that minimum energy required to leave. This is called the enthalpy of vaporization. The lower the enthalpy of vaporization, the more molecules will have enough energy and will have more molecules in that escaped gas and will have a higher pressure. This means that I can actually try and determine that enthalpy of vaporization, how hard it is for a gas to leave, if I know exactly how many more molecules I can get into the vapor phase by increasing the temperature. Because it will tell me, again, a lot about where that line is on that kinetic energy curve. So what we can do is try and plot vapor pressure versus temperature. However, it turns out they don't form a linear relationship. So it's going to be kind of hard to figure out enthalpy just from this basic sort of graph. However, chemists specifically, but most of the natural sciences in general, so biology and physics, tend to have a very constant reaction to when you see a graph like this. And that's saying, I don't know, can I linearize it? So linearizing it is a way of trying to turn this into a linear equation. So it's a straight line, and we can get all of the information we need out of a slope and intercept. And this practice pretty much originates from the days before computers. I could mathematically manipulate each of these points, so I could put it on a straight line, use my ruler, get the slope and intercept. But it still has a lot of use today. So what we need to do is figure out what sort of mathematical functions I can apply to the pressure and the temperature to get a linear equation. Now, it turns out that many equations which relate concentrations to temperature have a very kind of familiar form. And we'll see this periodically throughout the rest of the semester. And they tend to like forming natural logs versus inverse temperature. So we'll plot a natural log of our variable, in this case, pressure, versus 1 over T. Now, because 1 over T tends to be very small numbers, for convenience, we often multiply this by 1,000 just to make the axes, going from 2 to 4 instead of 0.002 to 0.004. Now, in this case, what turns out to happen is the slope is going to tell us a lot about the enthalpy of vaporization, and the intercept is going to tell us a lot about the boiling point. Now, both of these features are going to be very useful in describing the intermolecular forces of a gas and in just predicting everyday behavior of species. So what we can do is generate a linearized equation of natural log of our vapor pressure. Note in this case, P denotes vapor pressure, not total pressure or partial pressure, but vapor pressure. So if I let that liquid sit out long enough, versus 1 over the temperature the experiment is run at. The slope is going to be based on the enthalpy of vaporization and the ideal gas law. Note that all of those lines pointed downwards, and it will take energy to evaporate a liquid. So vaporization will be positive, so I need to put a negative sign out front. Then we have the big intercept. Well, it turns out that what we can do, and this is a useful sort of equation, but oftentimes what we want to do is if I want to figure out the pressure as well, I need to go ahead and use a reference point. So what we do is instead look at relating two different points. So I can relate the pressure, vapor pressure at a given temperature, T2, if I know 1 over other vapor pressure and 1 other temperature. So again, this equation can be derived from that original linear form, and we'll see a little bit of how later. Now again, remember that the ideal gas, R is our ideal gas constant, 8.314 joules, but make sure that you watch out so it matches the units of your enthalpy. This is one of the easiest ways to misuse this Clausius-Clapeyron equation. However, in order to use this Clausius-Clapeyron equation, it requires that I know at least 1 vapor pressure at least 1 temperature. If I'm trying to determine the enthalpy of vaporization, I'm going to need to know at least 2 pressures and at least 2 temperatures. But in practice, it's more common that you would just plot it and get the slope. However, again, usually I'm trying to determine a vapor pressure at a temperature, so I'm going to need another reference point. Thankfully, there is one reference point that is very easy to measure for almost every liquid, and that's the boiling point. So for this, we can actually finally define what boiling point is. So we know that all liquids will generate some degree of vapor. Now, what ends up happening if it generates a vapor, if it generates a gas with a pressure of more than 1 atmosphere? Well, at this point, what ends up happening is any gas that it generates now has enough pressure that it can push up on the liquid and escape. And this is the act of boiling. So a substance boils whenever the vapor pressure is greater than the atmospheric pressure. The boiling point is thus going to be when these two properties are the same. So any substance will boil when vapor pressure equals atmospheric pressure. So for consistency, most boiling points are referred to using what's called the normal boiling point. So vapor pressure of 1 atmosphere. And for water, useful to know this is 100 degrees Celsius, good old 373 Kelvin. So that's a good value to just have memorized if you don't already. So what we can do is, using that boiling point, we can kind of rearrange our Clausius-Clapeyron equation. Because remember, it was originally P2 over P1. But if our pressure 1 is 1 atmosphere, well, it disappears from the equation. And so all I have to do is include that reference boiling point. So then using this, we can separate out all of the boiling point variables. And since the boiling point is a known value for most liquids, enthalpy of vaporization, often known for most liquids, and ideal gas constant is a constant. What this does is it lets us put in a temperature that we care about and get a vapor pressure. Alternatively, if you know the vapor pressure, you can figure out the temperature of the system. However, there is a limitation of this form. We're assuming that the pressure in this case is in atmospheres, because what I did is I dropped out that P1 term. Remember, P1 is 1 ATM. So if you go ahead and switch to any other units, you have to use the other form where you explicitly put in your reference temp pressure in the appropriate units and make sure that they all cancel out. So that is a little bit of trick in using this formula. Now, it can often be used, this Clausius-Clapeyron equation can often be used to relate very important everyday phenomena. So one of my personal favorites that I do enjoy is it turns out that boiling point of water isn't always the boiling point of water. When you go up to very high altitudes, it turns out that the atmospheric pressure is much lower. Because remember, atmospheric pressure is only 1 ATM at sea level. If you go up a mile up into the air to Denver, Colorado, it turns out that the vapor pressure is, or the atmospheric pressure is 0.83 ATM. And since the atmospheric pressure is different, it means that the boiling point is different. So what's going to be the boiling point of water in Denver? So at 100, if we use the normal boiling point of water as a reference point, so 1 ATM and 100 degrees C, and the vapor pressure of water of 40.65 kilojoules, watch out for that unit, per mole. So we start with our Clausius-Clapeyron equation, and then we realize I'm trying to solve for temperature. So I'm going to have to rearrange it. Multiply by negative R over enthalpy, and then add in 1 over temperature. In this case, it's often easier if you solve for 1 over temperature instead of trying to inverse the whole right side. So when we do this, watch out for your units and make sure enthalpy and the ideal gas constant are in the same units. And as long as the pressure is in ATM, we should be fine. And again, temperature, always in Kelvin. So when you solve for this, it turns out 1 over the new boiling point temperature is going to be 0.0027 inverse Kelvin. Well, that's not convenient, so let's go ahead and do 1 over this number. And it turns out that the boiling point of water in Denver, Colorado is about 94.5 degrees C. So a little more than 5 degrees Celsius. So this would be about 12-ish degrees Fahrenheit lower than you would expect. And as a result, because water boils much easier at these high altitudes, they often sell what are called high altitude cookbooks, because it turns out you need to change all of the times on your recipes and some other things if you're trying to cook at a very different atmospheric pressure. So hopefully this gives you some enlightenment about some everyday phenomena. Next time, we're going to dive in a lot more detail on some other phase transitions, specifically focusing in on solid liquid. It's time to melt some stuff. Until then, take care.